You know when you walk outside on a sweltering summer day, you see those heat waves sort of shimmering off the asphalt.
Oh, yeah, where the air almost looks like it's boiling.
Exactly. Well, imagine shrinking that distortion down, amplifying the heat by like tenfold, and trapping it inside a room filled with tens of millions of dollars of delicate computer servers. So, welcome to today's deep dive, where our mission is exploring the invisible, high-stakes weather system happening inside data centers right now.
Right, and normally visualizing that kind of volatile weather requires massive enterprise-grade software. But the sources we're looking at today are just wild. It's a mix of raw Python code snippets featuring PyQt6 and OpenGL, and this fascinating voicemail from the tool's creator.
Yeah, a single engineer who built this custom 3D thermal simulation tool basically just to refresh his mind on HVAC systems,
Yeah.
which is crazy. He mentions drawing on his background with smart buildings at Johnson Controls and cooling systems for locomotives.
I mean, I guess when you're used to cooling down train engines, taming a server room sounds like a fun weekend puzzle.
A weekend puzzle that stops catastrophic server meltdowns. But to actually prevent those failures, this tool has to perfectly model the physical environment first, right?
Yeah, and he accomplishes that by writing a custom physics engine completely from scratch. Specifically, he uses an Eulerian-Lagrangian hybrid Navier Stokes fluid solver.
Wait, hold on. I recognize Navier Stokes from, like, aerodynamics.
Yeah,
Is he basically running airplane wind tunnel software inside a server rack?
he absolutely is. He's applying the exact same complex math used to predict weather and airflow, and the hybrid part is really the secret sauce here.
How so?
Well, the Eulerian approach looks at the big picture, right? It calculates the overall wind currents in the server room. But simultaneously, the Lagrangian approach tracks the specific microscopic path of a single drop of coolant or a distinct wave of heat.
Wow, so it tracks both the macro storm and the individual raindrops in real time. That actually explains the specific code snippets we saw generating vortex rings for turbulent mixing above the hot racks.
Yep, and the condensation particles that simulate cold fog or leaks. It really is a micro-weather system where 15-kilowatt rack heat emitters are just constantly clashing with liquid cooling nodes.
That's honestly visually impressive to think about, but just observing an indoor storm doesn't stop it from wrecking your house.
Exactly, and that's where the system steps in to fix the temperature autonomously using its AI brain.
Okay, let's get into the AI brain.
So the code contains this decision engine that utilizes aerospace-grade advanced PID control and feed-forward loops to lock in thermal equilibrium.
Let me just decode PID control for you listening for a second. It's basically like cruise control in a car. It doesn't just blindly slam on the gas or the brakes.
Yeah.
It calculates how fast you are approaching your target speed so you don't overshoot it.
Right, because in a server room, overshooting the cooling causes condensation, while undershooting obviously causes a fire. To support that delicate balancing act, the code also runs an incident analyst script.
Which does what exactly?
It takes raw telemetry, so thousands of temperature data points, and transforms them into structured semantic context. That way, a large language model, like Gemini, can process the technical reports.
Okay, here is where I really have to push back. I'm picturing an ER triage nurse metaphor here. The raw data is a patient's wildly fluctuating heart rate, and the script translates that so the doctor, which is the LLM, knows what to do. But LLM API calls take seconds.
They do, yeah.
So in a thermal crisis where servers are literally melting down, does relying on an LM actually speed up a crisis response? Or do we risk just generating a beautifully formatted, highly articulate report of a disaster that already happened?
That is a great question. The latency of AI in emergency loops is a critical factor, but the semantic translation isn't meant to delay that split-second PID cruise control we just talked about.
Oh, so they operate on different timelines.
Exactly. The PID handles the immediate physics. The LLM triage prevents human delays in the secondary response. So instead of an on-call engineer spending 10 panicked minutes deciphering raw charts, the system has already correlated the temperature spike with a specific node and suggested a rerouting protocol.
Got it. So the AI isn't holding the fire extinguisher, it's coordinating the fire trucks while the sprinkler system does its job.
That's a perfect way to put it. And those fire trucks extend far beyond the server room, actually.
Wait, really? How far?
Well, the code includes a supply chain orchestrator linking the simulation to major energy transition players. It directly integrates with ABB technology for automation, and it even lists partners like Taste CCS for carbon capture design.
Why would a solo HVAC side project need to talk to a carbon capture partner?
Because by connecting directly to ABB's energy grid tools, this tool isn't just cooling a room, it's calculating the exact carbon footprint of that cooling in real time. If it predicts a massive heat spike, it triggers a supply chain to temporarily shift power sources.
Wow, maintaining efficiency without overloading the local grid or spiking emissions. So for you listening, this deep dive really highlights a tool that beautifully bridges the gap between raw thermodynamics and AI-driven resilience.
Yeah, it gives engineers the ability to visualize cooling optimization and test fatal failure protocols via these interactive operational dashboards.
Right, tools to control the weather before the digital road melts.
It is an entirely new way to look at how we manage the physical infrastructure that powers our digital lives.
Absolutely. Which leaves us with a rather provocative thought for you to mull over. If a single engineer can build an AI-driven digital twin capable of managing data center thermal equilibrium, just to refresh his mind, how long until these autonomous digital twins are trusted to entirely design, build, and operate our critical physical infrastructure without any human intervention at all?